a video for Advanced Algebra 1, Topic 5, Section 2, graphing piecewise defined functions. And we start off right off the bat with, why do we need a piecewise defined function? And the reason we need it is so that we can define absolute value as a piecewise function. Because when we get into higher mathematics, that rate of change that we're talking about, being the slope of the line at between two given points, becomes where we do that instead of finding slope, we find the derivative. And we don't have a rule for the derivative of absolute value. But if I split it up and I write it as two different functions, then I do know how to take the derivative of that. Okay? So the way that works is, here I have f of x equals 2 times the absolute value of x. And, we've already gone through, I plug in 0, I get 0. I plug in 1, I get 2. I plug in -1, I get 2, and so on. Okay? But as I said, we want to define this as a piecewise function. And so what we do is we put f of x equals, and then we put a big brace, and for the top, okay, for this one, we put 2x for x greater than or equal to 0. And then for the bottom function, we put -2x for x less than 0. And I put less than 0 there because I can't have equal to in both places. Okay, so I put equal up here and less down here, and that's really all there is to it. That's how we apply the definition of absolute value to this function, absolute value. This is how we change it from here to being a piecewise function with no absolute value, and then we can take the absolute value or the derivative of this now. We can also graph that. I'm going to use the equation for the line 2x when x is bigger than 0 and bigger than 0 positive. So again, that'll give me the same line. Goes through the origin. The slope is 2, rise 2, run 1, rise 2, 1, run, etc. And there's that part of the graph. And then rise 2, run -1. Rise 2, run -1. And there's the other side of that graph. Okay. Realistically, for absolute value, we're not gonna define it as a piecewise function and then graph the function as a piecewise function. We know how to graph this as absolute value. We still need to know how to apply that definition. And so you will have some questions like this in your homework. There'll also be a question like this on our quiz over this section, and probably on the chapter test as well. Okay. So what if that coefficient out there is negative? Well, as I said, we start off with keeping it the same, so -3x, and when we keep it the same, x is greater than or equal to 0, and then the opposite of that would be 3x when x is less than 0. So what that does is it puts, our intercept for this top one is still the origin. I'm going to rise -3 and run +1. Rise -3 and run +1. Then for the other side of it, I'm going to rise -3, run -1. Rise -3, run -1. And that gets me this graph. Okay. Again, the most important part here is understanding how to take it from absolute value and use the definition of absolute value to write it as a function, a piecewise function. Okay. The other part of this homework is just real It's real fun for me. I like piecewise functions. They're pretty cool. They allow us to talk about a lot of things in calculus. Maybe that's why I like them. And so, and that's part of why, we're preparing you for the future. That's part of why we study it in Algebra 1. So, notice that this is x is less than or equal to 2. This is x is greater than 2. And what I do is I call that my swing point, okay? Because that's where I'm going to change the definition of the function, okay, is at 2. So if I make a table, which, is just to show my work and x plus 1 and what the y value would be. For this rule, I'm less than or equal to 2. So I'm going to plug in 2, 1, 0, negative 1 maybe, okay, because I want to plug in numbers that are less than 2. When I plug in 2, I get 2 plus 1 is 3. 1 plus 1 is 2. 0 plus 1 is 1. And negative 1 plus 1 is 0. Okay? And I can plot those points. 2, 3, and I'm going to put a solid circle because that's less than or equal to. And then 1, 2, 0, 1, negative 1, 0, and it keeps going, right? Keeps going in that direction. It does not keep going in this direction because it's only defined for less than or equal to 2. I'm going to do the same thing, but my equation here is negative 3 halves x plus 6. Hopefully I can make this fit on our graph. Y. So again, I'm going to start with 2. But, so I plug in, I get negative 3 halves times 2 plus 6, I get 3. Okay? So when I go to plot that point, 2, 3, it lands on the point that's already there. If it had not done that, wherever it landed, I would have put an open circle because it's strictly greater than, not greater than or equal to. Okay? Now I'm going to plug in, I'm not going to plug in 3 because that's going to give me a fraction. I don't want to graph a fraction. So I'm going to plug in 4. And so I get negative 3 halves times 4, which is plus 6, and I get 0. So 4, 1, 2, 3, 4, 0. And then I'm going to plug in 6. So let's see, negative 3 halves times 6 plus 6. That's going to be negative 9 plus 6, negative 3, I believe. So 4, 5, 6, 1, 2, 3. And so here is that piecewise function. Okay. That's pretty cool. And obviously the domain, because this got filled in, the domain is all real numbers. The range is from here down. So the range is y is less than or equal to 3. Domain, of course, was all real numbers. And that's it. By the way, we could not write this as a absolute value problem because the slopes are different. In order to write this as an absolute value problem, the slopes would have to be the same. Okay. And I have one more example for you. There you go. My swing point this time is 1. Okay. So my first defined function is x minus 2. And that's for x is less than or equal to 1. I'm going to plug in 1. I get negative 1. I'm going to plug in 0. I get negative 2. I'm going to plug in -1 to get -3. And then my other function is defined as -2x plus 3. And even though it does not equal 1, I'm still going to plug in 1 because it's my swing point, and I need to know what that graph is doing at 1 and just to the right of 1. So I plug in 1, I get -2 plus 3 is positive 1. Plug in 2, and I get -4 plus 3, which is -1. I plug in 3, and I get -6 plus 3 is -3. So for this left one, I plot the point 1, -1, 0, -2, -1, -3. Just like the other one, it keeps going. Okay. The other one, I plot 1, 1, and I put an open circle there. And I put an open circle because this is strictly greater than. I didn't have to do that on the other one because it matched up. Okay, this one it doesn't. So the closed circle is here, open circle is here. And then I plot the point 2, -1 here, and the point 3, -3 here. So that's the other side of that graph. Okay, and again, I'm going to reference calculus. What's happening at this swing point, we call that a jump discontinuity. Okay, this function is not continuous. In a continuous function, I can trace the graph without lifting my pencil. Okay, a continuous function, I can trace that graph without lifting my pencil. In a discontinuous function, I trace this graph, I have to lift up my pencil, go to this graph, and then trace that graph. So this graph has a discontinuity, and specifically we call this a jump discontinuity. And when we get into calculus, we'll learn that you cannot take the derivative at a jump discontinuity. But we can amend our piecewise function and fill in that hole so that we can find the derivative. We have all kinds of tricks for handling that kind of stuff in upper mathematics. That's really all there is for this video. Online homework next, and ask questions if you need help.